Hello and welcome to part 5 of Dev Maths and Stats Refresher Course, Lecture 7. Now we look at random variables, and by random variable we just mean any variable that can take on a range of different values, and there's a probability that it takes on each possible value, which is given by a probability distribution. We can distinguish between two types of thing. There's a discrete random variable and a continuous random variable. So discrete random variable, most well-known example is when you roll a die. So when you roll a die, possible values of the random variable are 1 to 6. Each value has a probability of 1 in 6 occurring for each time you observe it. So each time you observe means each time you roll the dice. Each time you do that, you have a probability of 1 in 6 for each outcome. What assumption is necessary for this to be true? Clearly the assumption is, trying to think about this first, but it says that it's a fair dice, so it's not loaded. Continuous random variables have a slightly strange feature. So take a simple example, a continuous random variable, and it can take any real value a, so any numeric value a, where a is greater than or equal to 10 and less than or equal to 30 with equal probability. So question for you is, if you understand that situation, what's the probability that on any one instance of this, if you, like when you throw a dice, you choose a value of a, what's the probability that a, when you choose a value, takes the value 18? Okay. So have a think about that. I'll just try and illustrate it. Okay, so there's 0 and 30. You can choose, was it 30? It was, yeah. No, I know what that was, 10 and 30. So 10 and 30, this is A. A can take any value between 10 and 30. So what's the chance that it takes the value of 18 exactly? So maybe here's something that just below 20, so 18. What's the chance it takes that value exactly? And the answer is the probability that A is 30 is equal to 0. Because there are, in terms of the number of different values between here and here is infinity. There's an infinite number of different values. The chance that it takes any one of them is 0, which is a bit strange. Kind of philosophically hard to get your head around, but there it is. But that doesn't mean that you can't work with these things. I'll show you how you work with them in a moment. Because of this, they have an infinite number of values. You can't just kind of write out the probability of each possibility because it's 0. So what you do is you have an idea of something called the probability density function. Then the area under the curve measures the probability. So I'll draw it. So examples of that in a minute. The stars mean it might need some calculus, but we've all done calculus, so we're good with this, especially integration. So if you've got a variable x, a random variable, can take different values at random. If the probability density function is f of x, then the probability that an observation is between a and b is given by, you have to integrate the values of x between a and b and integrate f of x. So integrate f of x for all values of x between a and b. That gives you the probability that it's going to lie between a and b. So example A, identify, oh sorry actually, oops, there's one more part here. What does this tell you about the value of, for any probability density function, of the integral between minus infinity and plus infinity? Think about that. Maybe I'm going to draw this example first. So I'm going to draw, if you haven't tried this, see if you can do that. What are the probability density function for this random variable A look like above? And I'll just draw that one out. So this is for random variable A. It's better. Just trying to spare you my handwriting for once. So A can take any value between, I think it was 10 and 30. Now if I draw f of x, which is the probability function, it would have to look something like this. Come along here, and it's at 0 here, because you're not allowed to go below there, and in actual fact you can just draw to infinity down here, and to infinity up here. But in between, it would be dead straight like this. I'll try and draw it straight, dead straight, rather than ruler. Oops, slightly messed. So the probability density function would be something like this. And the idea of this is that to calculate what's the probability of it being between any two numbers, you just integrate, which, as you should know from the integration lecture, it gives you the area under this graph. If you integrate this between any two values, you get the area under here. So if you integrated this between 10 and 15, so that's 15. If you integrated that, it should give you the probability that A comes out between 10 and 15. And obviously, because it's evenly distributed, it's got an equal chance of taking any number. That should be 50% or 0.5. So the key thing you know about this graph is that the total area under the graph from 10 to 15 must be equal to 1. So that area is equal to 1, because these are all the possibilities. It's not allowed to be less than that. It's not allowed to be greater than that. But in fact, for any probability density function, if you found the total area from minus infinity to plus infinity, which is what this is asking about here, that's the total area from minus infinity to plus infinity. That must always come out as 1. So this always comes to 1. So you know this is 1 here. Because you know it's 1, you can actually add a bit of extra detail here and say exactly what this height is. Because this is a length of 20, this way. And 20 times this must be 1. So this must be 1 over 20 here, that height. And then you can calculate any probabilities. You can calculate the probability of it being between any two numbers by looking at a slice of this and saying how big it is. Okay, let's look at one with a slightly more interesting probability density. No. So I paste that in here, and this is question 2. Just doing this to save, trying to draw, so you can see it more clearly. So here's 2. If this is a probability density function, and we know it can only take on values between 0 and 10, so it's 0 outside of here, we can then calculate the height of m, because we know the area, total area equals 1, so a half times base times height. Hopefully you remember that from school maths. So it's going to be a half times the base of this is 10 times this mystery number m. It's going to have to be 1. So m is going to have to be 2 over 10, which is going to be 5. This is unlikely. It's going to be 1 over 5. Yeah, so it's 1/5. So if this is a fifth, 0.2, then that works out. Yeah, okay, there's another question on this one. Okay. Find the probability that B is between 2 and 3. So here's, oops, 3, and here's 2. I'm sure it's drawing that to scale. 2. So a couple of different ways you can do this. You can subtract heights of triangles, or you can use parallelogram, the parallelogram formula. But either way, you're going to have to know the height of this. So the height of this is going to be, if this is 0.2 or a fifth, it's going to be 3/5 of a fifth. Is the height to here. And this is going to be 2/5 of 1/5. Height from here to here. So parallelogram, probability that x, if equal to x, is between 2 probability that x is between 2 and 3 is equal to area of parallelogram. This parallelogram here, I'll draw in maybe red. So you want this area here. Which is the average height. So it's half of this plus this. So these are over 25. So 2 over 25 plus 3 over 25. 2 plus 3, 25. That's the average height. 2 over 25, 3 over 25. Divided by, multiplied by the distance between them, which is 1. So we're looking at, this comes to 5, so it cancels out again. 5 over 5 is a fifth, so 2 times a fifth is a tenth. So there's a 1, I don't think I'm drawing it correctly. So there's a 1 in 10 chance of it coming in this area here. Okay, so there's just 2 more questions here before we get to the multivariable situations. So these I put stars on because they're slightly harder, so I don't think I'll put this probably on the test, but it's the sort of thing that you might like to be able to do. So if you don't want to do these with calculus now, oh, I know it's not actually showing on the screen. Sorry. These have got stars because they're slightly harder. If you want to skip these, that's fine, but I'm going to go through these 2 now before doing this in the next video. Let's grab both parts of that. So I think here, just carry on. Great. So it doesn't say to draw it, but I'll just sketch what's going on. So this is an exponential probability function, probability density function. So x is increasing this way, and it's e to the minus x. So it's the same as the graph of e to the x going like this, except because it's e to the minus x, it's coming down like this. It's hard to draw, but it's going down like that. Ooh, it's close to 0. And this side it would go up like that. But for probability density function, you can't have it going like this because the area would be infinite. So it's got to be bounded. So instead, we've said the probability function is like this. It's 0 here. And then it follows this curve here. So that means that the area under this graph of equals e to the minus x is actually 1. Exactly 1. And as an aside, remember this is 1 here. If you remember, the gradient here is -1, the value is 1, and the area under the graph from here off to infinity, because it goes to infinity, is also 1. So the integral of the slope that's negative is still 1, and the value of the function is 1. Anyway, let's try and answer the question of that. These aside, so what you want to know is what's the probability that r takes a value between 2 and 3. So again, we've got 2 and 3 here, it's not very original. And we need to know this area here. So this is the area we're interested in. That will give us the answer to the question. And that area is probability that x, well, you can put x or r, but lazily putting r already. Lazily putting x. If it's bigger than 2 and less than 3 is equal to blue area. Which is, you have to integrate this function between 2 and 3. So that's integrating e to the minus x dx between 2 and 3 equals. So first you integrate it, so you know when you differentiate e to the x, e to the minus x, it's going to stay as e to the minus x. So you can try that, but this doesn't quite work because if you differentiate that, you multiply by the differential of this according to the chain where you get a negative coming out, -1. So you have to start with this. So when you multiply by the negatives, it becomes positive again, so that's correct. So put in 3, so you're going to have minus e to the minus 3 minus e to the minus 2. So put in this, you have minus e to the minus 3 minus e to the minus 2 and subtract them. So it's going to look better the other way around, e to the minus 2 minus e to the minus 3. So kind of awkward looking answer, but that's the probability. On a calculator, you can use the calculator, you can work out the decimal. And then 4, the cumulative probability distribution for the function r in the above example, that means a cumulative probability means if it gives you the probability that for any value, the probability that it's up to that value, so that value or less. So we can see that cumulative probability function most of this too quick. F of x equals gives you the probability that r is less than any value of x. So give me a value of x like 3, put it to here, it tells you what's the probability that r comes out as less than that value of x. And clearly we can see that if x is up to 0, then f of x is equals 0, because there's 0 chance it's going to be anything up to here. Then after you go past this point, you start to add up the area here as far as you go. So f of x is essentially this area up to the point x. So you integrate all the way up to x. So for x positive, f of x is the area under f of x. So between 0 and x of this. So it's the integral from 0, or from minus infinity, well no, from 0 up to x of e to the minus x. So integration as before, this is as before, so it's just different limits. So we can switch them around, so it's going to be x, so it'll be minus e to the minus x, and this comes out as 1. Minus 1, but the 1 will be positive, so it's 1 minus e to the minus x. And you can tell from this what happens as x gets bigger and bigger and bigger and bigger, this becomes smaller and smaller and smaller, and it becomes closer to 1. Because clearly, as x gets bigger and bigger, the chance that it's less than that becomes closer and closer to 1 because all the area is used up. Does that make sense? So this is the cumulative probability distribution function, the probability for any x that the value you choose is going to be less than that value. Okay, so the final, it could be the final, I'm not sure, but the next session we're going to look at multivariate probability density functions. So that's when you have 2 variables or more. Okay, but for now, thanks for watching.